All right, good morning, class. I guess it could be afternoon depending on when you're watching this. We're going to finish up Stokes' theorem, do two more problems today. This is just the next page of the notes. We finished up with finding that the left and right side of the equation for circulation and then the Stokes' theorem match. So now we're going to do two more problems to show you how to use Stokes' theorem. Again, these are used when you're looking for circulation with a field. Everything else is kind of like what we were doing in 8.2 with the surface integrals, all the pieces you need. So for this problem, it says find the circulation of the field, and this field given is actually the one that was at the beginning of your notes where I said just find the curl. So the good news is we already know the curl of this. So we'll put that down in a second. In fact, I'll put it down right now because we have it. So why not? So the curl of f, I should probably say of f, is equal to, and it was this vector, it was -4, -2x, and then 1. Okay. So now let's look at what the shape is and what we're seeing. So it's around the curve in which the plane z equals 2 meets the cone x squared plus y squared, the square root of it, equals z. So where that is that c, that means c is this circle here, which is the circle x squared plus y squared equals 4. The surface itself actually could be parametrized. I believe we did this with this problem earlier. You can come up with a parametric equation for the surface in terms of just r and theta, which is equal to, obviously x is always r cosine theta, y is equal to r sine theta, and then z is equal to the square root of that. Well, again, for this problem, x squared plus y squared equals r squared, which is just r. So that would be the parameterization of this thing. R will go from 0 to 2 because, again, we're going to the circle where the z equals 2 meets the cone, which forms that circle with a radius of 2. And since it's going all the way around the axis, the theta will be between 0 and 2 pi. So this is just something we did actually in the first day of this chapter. We are just parametrizing this cone, and I feel like we've done this one already. So yeah, this is from the last section. So what we need now is we need a few things. We need the normal vector. So the normal vector is always the cross product of each piece divided by its magnitude, because remember, a cross product gives you a normal vector. Now, again, we did this from the last section. I'm going to skip the work from this because you guys know how to do a cross product and take partial derivatives. We end up with that the normal vector is 1 over root 2 times negative cosine theta, comma negative sine theta, comma 1. Okay, so there's n. So we pretty much have n and the curl. We're going to have to cross those. Before we do that, though, notice how everything is becoming thetas and r's, which means we actually do have to fix this x right here. That'll actually just turn into an r cosine theta when we do our dot product. We have one more thing we need to find. We need to find d sigma to finish up the setup of our Stokes theorem, or the Stokes theorem, so the integration of the curl dotted with the normal. So d sigma, when we're in parametric, is always the magnitude of the cross product of the two partials, and then dr d theta or d theta dr. So again, from the last section, I should also put an arrow here, we get that the magnitude of the cross product is r square root of 2, and then we have dr d theta. So now we have all three pieces that we're going to need to set up our integral. We have f, we have to dot it with n, and then we have to attach d sigma. So first thing is we're going to do the dot product. So I'm going to say that my Stokes theorem is equal to now, or I guess I should say circulation. Let me actually write it like this. So we're going to be doing this now. We're finding the circulation again, this means curl, which we have, dotted with n d sigma. So we're going to set this up, and what this looks like is when you do the dot product of the curl and the n, the normal vector. By the way, before we even do that, notice how this root 2, remember when you do a dot product, this will stay on the outside, and then we have this piece with the d sigma. So I'm actually going to cancel those out right now without even worrying about them. You know, I'll keep it in case you guys get confused. So we have 1 over root 2, and then when we do the dot product, you get 4 cosine theta plus, and then this will become a plus because there's double negatives. We get a 2 r cosine theta sine theta, because remember this became r cosine theta, plus 1. We have the double integral from 0 to r is 2 and 0 to 2 pi for theta. So that is the dot product of the curl and n, and now I have to tack on d sigma. So we have an r root 2 dr d theta. So like I said, the root 2's from these parts can go away, and now we end up with this integral here, and then we just keep going. At this point it's just doing an integration. We have to distribute the r, so I get 4r cosine theta plus 2r squared cosine theta sine theta. Okay, now here's a little weird thing that I wanted to explain to you guys. This is actually an identity. 2 sine theta cosine theta turns into, believe it or not, which you should maybe remember from way back when, the sine of 2 theta. So I'm going to use that in the next iteration of my equation. So we have that plus r, and then that becomes dr d theta. Now we integrate with respect to r. So this becomes 2r squared cosine theta. Whoops. Okay. Then we get plus r cubed over 3 times the sine of 2 theta. Like I said, that's the change. Plus r squared over 2. And we're evaluating that from 0 to 2. So when you plug in a 2 into everything, the nice thing is when you plug a 0 in, everything will wipe out. Whoa, I don't know what that is. Everything will wipe out. So we just have to plug the 2 in. So one more real quick. Plugging the 2 in, we get a 4, we get 8 cosine theta. Plus we get 8 over 3 sine 2 theta. Plus that just becomes 4 over 2, which is 2. We're now doing d theta. So now we're integrating with respect to theta. We end up with 8 sine theta minus 4/3, because you had to divide by 2, cosine 2 theta plus 2 theta from 0 to 2 pi. Okay, so the circulation, if we plug all this in, 2 pi, sine of 2 pi is 0, cosine of 4 pi is a 1, and therefore we get a negative 4/3 plus 4 pi minus, and then we plug in 0, that's nothing, that's negative 4/3, and then we don't get anything else. So the negative 4/3, this will become positive, negative cancels. The answer is 4 pi. Okay? Again, the key is all in the front end of this, is the setup. Make sure that you have the correct n gradient of f, I'm sorry, the curl of f, not the gradient, and then d sigma. D sigma could involve the gradient of f or not, depending on which form you're using. This next problem, we are going to use the form where n is the gradient of f over the magnitude. We're using the implicit form. So it says evaluate the circulation. Again, there's the formula for circulation using Stokes' theorem. We have a field here in x, y, z. We have the boundary is this plane, So that's our curve in the first octant. So first thing we need to do, well, we could do a couple things. The normal vector is just the gradient over the magnitude of the surface. So the surface, again, is the plane. So it's going to be this equation here. So that's going to be 2, 1, 1 over, well, if you find the magnitude of this is 4 plus 5 plus 1 plus 1, which is 6, so this is root 6. So this is the normal vector. The curl of f, using the formula up above, if this is your m, n, and p, and using the formula from the first page, okay, using the formula from the first page, we get dp dy, there's no y there, minus dn dz, there's no z there. We have dm dz, we do have a z here, so when we take the derivative, we just get 3x, minus I'm sorry, I screwed that up already. dm dz is just x, minus dp dx, which is 3z. And then finally we have dn dx, which is a y, minus dm dy, there is no y, so that's 0. So that vector becomes 0, comma, x minus 3z, comma, y. So there is my curl, there's my n. Now we can also, the only problem here is you always have to get it in terms of 2 dimensions. Luckily, we can solve for z in this plane right here. So z is equal to 2 minus 2x minus y. So therefore, the curl is equal to 0, comma. When you do the math for this and plug this in, you get 7x plus 3y minus 6. And then this is still y. By the way, when I said when you do the math, did anyone else think of You Choose McGrath from the commercial? Or is it just me? I don't know. That just popped into my head. Anyway, lastly, we're going to do d sigma. D sigma is the gradient, the magnitude of the gradient of f. How am I doing time-wise? Ooh, I'm at 12:30. Over, again, the gradient of f dotted with p. Well, the nice thing here is p is, again, the shadow region is in the xy plane. So we are going to use p as 0, 0, 1. And since gradient of f is this vector here, that's just going to be a 1 on the bottom. And then the magnitude of this is root 6. So this is just root 6 over 1 dx dy. Alright, so we have everything. We now need to set up the integral. I don't know if I'm going to finish the integral today, but we are going to try to set it up, and then you guys should be able to actually do the integral yourselves. So the circulation turns into the double integral. Now, if I do dy first, because it makes sense to with this triangular shaded region. If I go in at the bottom, it's 0, and out at the top, it's this line y equals 2 minus 2x. That's just the shadow region. When z equals 0, you solve for y, and you get 2 minus 2x. And then x goes from 0 to 1. So those are my bounds for this. Now I do the dot product, and I do, so if I look at the dot product, I have the 1 over root 6 out here. That's the root 6 on the bottom. I'm dotting n with the curl, which is right here. So this with this. So I get 2 times 0 is 0. I get 1 times that is just that, so I get 7x plus 3y minus 6, and then I do 1 plus times y, so plus y. So it really should have been a 4y in there. That's fine. We also then have d sigma, which is root 6 dx dy. So what happens is these cancel, and this is our integral. Okay, I am going to run out of time here. So really, all you guys have to do at this point to do this problem is solve the integral. In fact, why don't you guys do that as your homework? Okay, I'll make that your homework problem. Just finish this problem. It'll just be a quick, easy Friday one, and then I'll give you guys problems for Tuesday, Wednesday, Thursday. All right, I hope you guys are doing well, and I will see you next time.